So I hope you realize not only that binary stars are cool, but that our understanding of the physics allows us to understand how we learn so much about them. As is the case with planets, if the inclination of the orbit is indeed zero, in the sense that the planets orbit in a plane that includes our line of sight, then something even more exciting is going to happen. Not only will we measure the full radial velocities, but halfway between those points where we measure the full radial velocities, just as with planets, one star will transit the other. And so there will be times during the history of transiting binary like this, where we see both stars. We can't resolve them, but we see both, and we see both sets of spectroscopic absorption lines. And then there will be times when we only see one of the two stars, or we see parts of one and all of the other. We see a non-trivial behavior of the light curve. And the light curve, as I promised with planets, will tell us things about the periods, the sizes, the temperatures of the two stars. And if we can combine this with Doppler measurements, we can learn a lot about the system. I want to spend some time looking at what we learned from a light curve, because I think it'll interest you, and I promised it when we did planets. Let's take a look at an eclipsing binary simulator. Eclipsing binaries are a rich source of information, and this simulator really allows you to play with them. So we see here on the left the perspective from Earth on a binary system of my choice. Note that this is not a perfect eclipse. There's a little bit of inclination of the orbit. That's because if I set the inclination to 0, we wouldn't quite be able to see what's going on. And we have here a star number 1, which is a large star. The radius is 3 times the solar radius, and it's a little bit cooler than the Sun. Its temperature is about 5,000 Kelvin. And I have here a smaller, hotter, bluish star, whose radius is a little bit less than the solar radius, but whose temperature is over 9,000 Kelvin. And, of course, as these orbit each other, I will plot on the right, or the system will plot on the right, the total intensity that we see from both of them. So the baseline is this situation where we see one combined star, which has the luminosity of both of them put together. And then there are dips. There's a dip here where the orange star transits and obscures the blue star, and there's another dip where the blue star obscures the orange star. So here, the orange star is obscuring the blue star, and note that this dip is pretty deep. Why is it deep? It's deep because the blue star being hot, we're losing sort of all of the luminosity of the blue star. The blue star completely disappears behind the orange star. The blue star being luminous gives us a deeper dip, and on the conversely, when the blue star transits in front of the orange star, we are losing some luminosity. We get a smaller dip right here. Why is the dip not so deep? Well, we're not seeing some fraction of the surface of the orange star, but since the orange star is cooler, even if it is on the whole more luminous than the blue star, that doesn't matter. The piece of it that is being obscured by the blue star is less luminous than the blue star itself, and so we see on the whole a little bit less light, but less than when the blue star transits. So the ratio of the depths of the two dips tells us, of course, the ratio of the temperatures of the two stars. Moreover, there's this flat region over here at the bottom of both dips. Note that it is approximately the same length, and would be if I set the eccentricity of the orbit to 0, which I wanted to do but forgot. Then the two dips would be exactly identical in length. Why would they be exactly identical in length? Well, modulo the inclination, because the length of this time is the length that the blue star is completely within the disk of the yellow star. And this, if the inclination is 0, takes the same amount of time on this side of the orbit as it does on this side of the orbit, because the geometry is the same. So what the length of this period down here tells me is the time it takes the blue star to transit completely the surface of the orange star, giving me a measure of the radii of the two planets. For example, if I know from radial Doppler measurements the speeds with which the planets are moving, I can convert this to a time, and I can tell you how long, I can convert this time to a distance, and I can tell you the radii of the planets. This is a measure of something like the sum of the radii, or some relation. What is this, the length of time over here tell me? Well, this is the length of time it takes from the moment that the planetary disks, as we see the star disks, as we see them in the sky, touch, to the moment where the blue star is completely engulfed within the orange star. So we start at this moment when we're starting the eclipse, and then we take the time until the star is completely engulfed in the larger disk. And so this time, again, gives me a measurement of the radius of the blue planet. The time on the bottom gives me a measurement of the radius of the orange planet. Of course, the period with which all this repeats gives me the period of the orbit. You can get lots and lots of good information. In fact, the actual shape of the dip here gives me some information about the nature of the atmosphere of the blue star, because which part of the blue star, or in the atmosphere of the orange star, because there's some overlap in the atmospheres before there's an overlap in the disks. We can look for spectra of the coronas of the two stars. We can get a lot of information. When the sizes of the stars are more comparable, then the structure is less clear, because then we'll barely get a dip when the orange star is eclipsed, but we'll get, I need to improve our inclination here so we won't see much, but here's a pair of stars that are orbiting with almost zero inclination, and again we see a deeper dip when the blue star is eclipsed and a smaller dip when the orange star is eclipsed. But in this case there's no flat period, because there's no time when one star, other than an instant, when we get maximal obscuring. And so the ratios of the radii and the temperatures can be read off from these plots. It's worth playing around with the simulator. I'm sure you'll learn a lot. So eclipsing binaries are a rich source of information. In general, we can learn a lot from binaries. The most famous example of eclipsing binary is, of course, as we call it, Algol, or perhaps Algol, which is the ghoulish-looking star in Perseus that dims for a few hours every few days, because it turns out it's an eclipsing binary. As we'll see later, there is yet more information that we can extract from binaries. Binary stars, as I like to call them, are a star with a built-in probe, and we can learn a lot about both members of the pair because there's something for them to interact with. So we'll come to binary stars again and again as the class goes on. For now, let's observe that our friend Alpha Alpha Corona Borealis happens to be a double-line eclipsing binary with a period of about 17.4 days, and we can do the Doppler measurements. Again, I quote in the credit section the paper from which I lifted these data, and it would be fun to go and read the paper, and you can see that you can learn a lot from that. Doppler measurements give me the radial velocities of the two stars, and I give here the speeds as we measure them. I plug into our formula for the masses of the two members of the binary. Of course, this was our formula for M1. Replacing every 1 here with a 2, I get the formula for M2. And I predict that Alpha is a pair of stars, one with a mass 3 times the solar mass, one with a mass approximately a solar mass. I can compare this with my spectral measurements. Since it's a double-line binary, I see the spectra of both stars. Indeed, we talked about Alpha Corona Borealis A last time. We said there was an A-type star. That mass of 3 solar masses and a radius, we said then, of about 3 solar radii is about right for an A star. Alpha Corona Borealis B turns out to be G5V, which makes it a little bit cooler than the star. Its radius than the sun, I mean. Its radius should perhaps be a little smaller, but another main sequence star. You can read about the light curve fits in the paper that I quote. You can also see how life is never quite as simple as what I presented in this idealized scenario. In particular, for example, the eccentricity of the orbit is very high, so our circular orbit calculation is bound to be a little bit inaccurate. In fact, from the paper, including both the eclipse data and the radial velocity data, the best estimate they find is about 2.6 solar masses for A and 0.9 solar masses for Alpha Corona Borealis B, a radius of about 3. We got that right, because temperature and radius don't care for radial measurements. So indeed, the radius of Alpha Corona Borealis A is 3 solar radii, and of the secondary 0.9. The temperature we had right for the primary. The secondary is about the solar temperature, and the little ratio of luminosities. The luminosity in units of the solar luminosity is what you would expect from their spectral type. The beautiful thing is, yeah, these people did some very careful numerics, but we understand and can actually emulate at least the physical principles, if not all the details, that went into this calculation. I hope you appreciate how much you've learned.